Start. So this one is ये क्या हो गया? Okay. So this is the slide which I showed last time also. What we are doing here is we are trying to understand the product operator formalism to describe the density operator. Density operator can be used to describe all kinds of situations, equilibrium and non-equilibrium situations. This slide is showing you the product operators for a two-spin system. What is the meaning? We would like to repeat here once more. So I will write this what we had written in the general formula of density operator was, we wrote the density operator as the summation of Bs into capital Bs. This capital Bs were the basis operators. There were 4 for one spin, there were 16 for two spins, and these are there consist of single elements and also products, two kinds of work. What is the meaning of this? We have to understand what is the meaning of these product operators to be able to interpret what comes out in the end. Okay, so in order to understand this, how do we know what these individual basis operators mean? So let's look at the density operator feeling once more again. For a two-spin system, we had the density operator, it was written like this. So we had the populations along the diagonal, and we had the various coherences here. In the off-diagonal element, they were the coherences. So therefore, and this was a 4x4 matrix. For a two-spin system, this was a 4x4 matrix. Now Bs is a constant, this is a number, and the product operators are the Bs. Therefore, the Bs also will be 4x4 matrices. Each of the Bs will also be a 4 into 4 matrix. And what it contains will be a part of the density operator, right? So these are all this together, they'll constitute the density operator. So therefore, it is possible that the Bs will contain some elements of this density operator, the rho. So that gives us an interpretation as to the physical meaning of what these individual basis operators are telling. Okay, so therefore, that is what we will try to explore a little bit more in detail today. Okay, so let us look at this. For the two-spin system, we have the one-spin operators Iz, Ix, Iy, and then there is also the unity operator E, which is always required. Okay, because you have to define the products and the inverses of all of those operators, which has to have the unit operator should be there, E. And then you have these product operators 2x, 2lz, 2k, 2ky, lz, things like that. Various kinds of product operators are there, which I described earlier. Now we are going to look at these individual products now and see what they actually represent. What they represent in the density operator, the rho, okay, that gives us the meaning as to what is the physical meaning of these individual basis operators. Okay, now here is an example. How do we calculate this, what these individual basis operators are? How do we calculate the matrices of these individual basis operators? So if you look at this, for this, these are for the one spin here, these are for the one spin. They are basically, the unit operator is, unity matrix is E, then you have the Ix is this 0, 1, 1, 0. This is the basically half of the Pauli matrices. Okay, Ix, Iy, Iz, these are individually represented in this manner for the one spin. So you can see here, the Iz operator has only the diagonal elements. So that means Iz operator is telling you of the populations. And if you look at Ix and Iy, they contain off-diagonal elements only. There is nothing on the diagonal. Therefore, the off-diagonal elements are telling you about the coherences. Okay, this is the Y component of the coherence. This is the X component of the coherence. In the sense, these represent therefore X and Y magnetizations. Now, for the two-spin system, there are 16. There are operators like IKX, ILX. Okay, what those ones are? How do we calculate the 4x4 matrices for these ones? For the unity operator, there is no. We use the trick of what is called as the direct products. So, for example, for the E, direct product of 1 into 1. So, what is basically that gives you a diagonal here 1, 1, 1, 1, 1. All others are 0. This is the unit matrix for the two-spin system. Now, for the IKX, what we do, I am putting the energy level diagram here once more. For convenience, I put the energy level diagram. The levels are 1, 2, 3, 4, and these are alpha K, alpha L, alpha K, beta L, beta K, alpha L, and beta K, beta L. Now, in this IKX, let us look at the operator IKX. What does this mean? So here, to calculate that into a 4x4 matrix, what I have to do is, I take this one spin Ix operator, and take a direct product with unit matrix. Half 0, 1, 1, 0 into direct product with 1, 0, 0, 1. How do you take the direct product? So therefore what you have to do is, direct product means if you take this in the place of 0, I put this entire matrix here, multiply this by 0. Whatever is present here, multiply this entire matrix by 0. Similarly, that gives me 0, 0, 0, 0 here. For the second one, I multiply at the position 1, in place of 1, I put this entire matrix. In other words, I multiply 1 with this entire matrix. So I get here 1, 0, 0, 1. Similarly, for this one, this element, again the whole 2 by 2 matrix comes. Each of these elements is represented by 2 by 2 matrix. So 1, 0, 0, 1, and the last one is again 0, 0, 0, 0. Now what we have got here, therefore, these are the elements 1, 2, 3, 4, right? These are 1, 2, 3, 4. These are the elements. And the column, therefore, in the side wise also 1, 2, 3, 4. So here what we see, 1, 3 element is non-zero. 1, 3 element is non-zero and 2, 4 element is non-zero. And these are the other components, the symmetry related things there. Okay. So 1, 3 and 2, 4 are non-zero. 1, 3, 2, 4 are what? This is this and this. Okay. So therefore this represents these two coherences. 1, 3 and 2, 4. It represents these two coherences. And both have the same sign. Therefore, I represent them as going in the same direction here as positive. The same side. So this is the representation of the IKX operator in a 4 by 4 matrix. Similarly, for the ILX, what I do, I just change the reverse order. So I first put the unit operator, I first put E here, and then I put the ILX, one spin operator, one spin X. So therefore, in place of 1, therefore I put the entire matrix 0, 1, 1, 0. Now for 0, I put here 0, 0, 0, 0. 0 multiplied by this matrix gives me 0, 0. And similarly, 0 multiplied by this matrix gives me 0, 0, 0, 0 here. And the last one is 1 multiplying this whole matrix, I get 0, 1, 1, 0. Okay. So now therefore, what I get here? Once again, I write here 1, 2, 3, 4. And these are related to K. Okay. These are K. And now what are the elements which are now 0? I see here 1, 2 and 3, 4. 1, 2, 3, 4 are this one and this one. So these two they are both positive. Therefore, this represents a matrix like this. So the ILX operator represents coherences 1, 2, 3, 4 in the total density matrix. The total density matrix represents these two coherences. So therefore, now I take the sum of these one, I get the total X magnetization. Therefore, this is the X magnetization, all right? The ILX, we are talking about the X magnetization. Therefore, single quantum coherences 1, 2, 3, 4 and 1, 3, 2, 4 and 1, 2, 3, 4. These things what we have. So these represent the X magnetization of the K and the L spins. Now, if I take the sum of this, I get the total magnetization. I get the total IX. What is the total IX? Therefore, you see this representation here 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. This is my entire IX operator, IX representation in the 2 by 2 matrix. Okay. So similarly, I can calculate for Y. Now, what do I do for Y? Now I have to use the one spin Y operators. IKY I should do. Earlier I used IKX. Now I will use IKY. So IKY is this is the one spin, and this is the unit matrix here. So therefore I get here 0, 0, 0, 0 and minus I multiplied by this unit matrix, minus I 0, 0, minus I, and I 0, 0, I, and 0, 0, 0, 0. Okay. So this is for ILY. Now notice here, therefore, these ones have imaginary numbers. Earlier they were real numbers. Now these are imaginary numbers. So imaginary number, this is basically to say these are 90 degrees out of phase with respect to the X or the Y. When you are talking about X and Y, these are 90 degrees out of phase. If you take the X as the real, Y is the imaginary. And that's why it appears in this manner, Y minus I minus I. Similarly for ILY, I do the same trick. I put E here first, and then I put this IL, the one spin I matrix. So I get here 0 minus I 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 minus I 0. Okay, so in principle, therefore, again you can calculate the total Y magnetization, IKY plus ILY. You get here 0 minus I 0, I 0 0 minus I 0 0 minus I, and 0 I 0. And this is the difference between the X and the Y magnetizations of the two-spin system. How to represent these magnetizations in the density matrix. Okay. So this is how we interpret this now. If I have a simple operator IKX, I say these are the elements of X magnetization of the K spin, because that is what they are representing. So if I look here, KY, what was KY? 1, 3 and 2, 4, that was the same here. This is 1, 3, 2, 4, this was the K, and these are for the L. These are 1, 2, 3, 4, these are the L, but these are now imaginary. Imaginary meaning what? What does it mean if it is imaginary? Okay, let's come back to it. Imaginary means it will have 90 degrees out of phase with respect to the X magnetization. If I take X magnetization as representing absorptive lines, okay, then the Y magnetization represents dispersive lines. Okay, so in this case, if I were to draw this as absorptive lines for the two, if I call this as absorptive lines, and then in this one, I will say these are dispersive lines. Okay, so because these are 90 degrees out of phase with respect to that one. And similarly for the L, you can do that for the L also. Okay, now IKZ, ILZ. How to represent IKZ, ILZ? Again, I do the same thing for IKZ. I take the Z magnetization of one spin and take a direct product with 1, 0, 0, 1. So I get here 1, 1, minus 1, minus 1. All other elements are 0. Okay, because it is 1 is multiplied by the unit matrix and the minus 1 multiplies the unit matrix here. All other elements are 0. So similarly for the ILZ, I turn it around and put here unit matrix here and the Z magnetization here. So I get 1 minus 1, 1 minus 1. Okay, so therefore this is how you get. Now if I want to do IKZ plus ILZ, I have to simply add these two. So what do I get there? What do I get there? I get 1 here and minus 1 there. Everything else is 0. Okay, so because those two numbers will cancel. So this one cancel with this will cancel with this. The only thing that remains is 1 and minus 1. Of course, you'll have this factor half. So this is how you get the total representations of the individual spins and also of the total sum of the two spins. Let's do the same thing for 2 IKX ILZ. That was since the individual one spin. Now we have two spin products. Two spin products. So therefore, what I have to do is I don't need the unit matrix here. I take the KX here and Z here. Okay, because these two belong to different spins now. This belongs to the K, this belongs to the L. So I take the direct product of these. So therefore, what I get? I get here 0, 0, 1, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, minus 1, 1, 0. Now, if you look at the energy level diagram of the previous one, this is again the same 1, 3 and 2, 4 transitions, right? These are 1, 3 and 2, 4 transition. But notice this 2, 4 has opposite sign compared to 1, 3. Okay, therefore X magnetization we say is antiphase with respect to L. That's why we get here, if there are two transitions 1, 3, 2, 4, I will get here like this. If this is 1, 3, then 2, 4 will be like this. Because these two will be, so this will be 1, 3 and this will be 2, 4. They have opposite signs, and this is the complement, the mirror image of that in the same one. And if I do the IKY ILZ, do the same thing. This is K, this is K, and this is L. So there is Z of L and Y of K. So I take this one here. So what I get? Again, I get the same elements, but now the imaginary numbers, because this is Y magnetization. So therefore, minus I here, I minus I here. So this is complex conjugate on the other side. Therefore, what I get here for the 1, 3 transition, I get a dispersive line and okay, now this was to be minus. Okay, now other one I will have to put. This is also So if one of them is positive, other one has to be negative. So this is how you get the two signs of the 1, 3, 2, 4. Okay. And this will be now imaginary, and this is now, so I actually put the other way around. So I should have put minus I is, so I'll put this one as 1, 3. I'll put this one as 2, 4. Okay, order is changed completely, but doesn't matter. So, so this is how you get the X and the Y components of the magnetization for a two spin. This is how, what does this represent? Now this represents, this is X magnetization of a K spin antiphase with respect to L. So this is the real numbers. This one is Y magnetization of K spin antiphase with respect to L. Okay. Yeah, so this is the same thing which I showed in a little bit more detail. I explained there. I put the energy level diagram here. And energy level diagram, I'm showing this. When I say positive and negative, what I'm trying to indicate that in the energy level diagram. So whatever is positive, I take it as thing which is going up like this. Whatever is negative, I take it as thing which is coming down like this. 2, 4 is coming down and 1, 3 is going up. So it is absorptive and emissive, absorptive line shapes, Lorentzian line shapes. And similarly for 2 IKY ILZ, I say the same thing here. So the two dispersive line shapes with opposite signs, and one is coming negative, 1, 3 is negative, it is coming down here, and 2, 4 is positive, which is going up there. So these are the Y magnetizations of K spin antiphase with respect to L. So explicit representations of the individual basis operators, you will get it like this. Okay. So now let us look at things a little bit which are more complicated, not quite complicated, the same way we can treat them. Take the product 2 IKX ILY. So what we do here is I take this as K, this is the X, 0, 1, 1, 0, and this is Y, 0 minus I 0. Okay, this is for L. So I take the same direct product once more. The direct product, once I take it, then I get here 0, 0, 0 minus I, 0, 0, I 0, 0 minus I 0, 0, I 0, 0, 0. Now in the two spin state, what do these elements represent? These represent double quantum. This represents a double quantum, the other representing double quantum, and this represents a zero quantum. This is double quantum and this is zero quantum. Therefore, this representation 2 IKX ILY is the sum of double quantum plus zero quantum coherences. All other elements are zero, nothing else is non-zero there. Okay, so the double quantum plus the zero quantum coherences are non-zero. These elements are non-zero. Now if I take 2 IKY ILX, so I have to do a K here. This is K and this is L. The things are interchanged there. Okay, 0 minus I 0, 0, 1, 1, 0. What do I get here? 0, 0, 0 minus I, 0, 0 minus I 0, 0, I 0, 0, I 0, 0, 0. Now we see this is exactly opposite sign compared to this so far as the zero quantum is concerned. This is the top minus I and I. These elements are the same. This and this are the same as on the top. But the zero quantum elements, they have changed sign. Okay. So what was I there has become minus I. What was minus I there has become I. So this is like multiplying the zero quantum by minus 1. Therefore, this represents double quantum minus zero quantum. Okay, is multiplied by second. So 2 IK, although both are mixtures of double quantum and zero quantum coherences, but there is a difference in the signs of the individual contributions in the two. So therefore, this actually gives a very clean way of getting pure double quantum. What is pure double quantum? How do I get a pure double quantum? We can immediately guess here. What we can do is, if I take the sum, 2 IKX ILY and 2 IKY ILX is here. So if I take the sum of these two matrices, I get here minus I and I. So 2 IKX ILY, 2 IKY ILX represents pure double quantum coherence, if there is an element like that. Okay. This is by addition of the two. I simply add this. I can do the same thing by subtraction. What I do, I subtract this. Subtract these two matrices. So I get here only I and minus I. So 2 IKX ILY minus 2 IKY ILX gives me pure zero quantum coherence, but the Y component. Okay, these are the, because these are all imaginary. Remember, these are I and minus I. These are imaginary numbers. Where there are real numbers, we take it as X component. Where it is imaginary, we take it as the Y component. So therefore, we define here the pure zero quantum Y component. Although physically you cannot talk about zero quantum along with the Y axis or along the X axis. But this basically to say these are the real and the imaginary components. That's what we want to say. To present in the classical way, to say it as X and Y, but really to say that these are the real and imaginary contributions, components of this. So this is pure zero quantum and previous was the pure double quantum. Okay. Now let's see what happens if I take the other kind. Now 2 IKX ILX. There I had considered earlier IKX ILY. So what I do now, I do IKX ILX. Okay, IKX, this is IKX, ILX. So both are the same here, right? K and L. Take the direct product. Once again, I get the same 4 by 4 matrix, but now 1, 1, 1, 1 along the double quantum and the zero quantum positions. Okay, this is again a sum of double quantum and zero quantum, plus these are now real numbers. In the previous case, they were imaginary numbers. Here they are real numbers. Okay. And similarly for IKY, ILY, when I take this, so this is for K and this is for L. So I get here minus 1, 1, 1, minus 1. Okay. So essentially the double quantum portion is multiplied by negative numbers. Okay. So one of this one is negative number. Or zero quantum minus double quantum kind of a thing it is. Okay, turn it around. Okay, so now what we can do is those numbers are changed into sign. Now you can add or subtract these ones once again. So if you do that, what do we get? 2 IKX ILX plus 2 IKY ILY. If I did that, what do I get? If I add these two, then I get only 1, 1 here. So at the zero quantum position, I get 1, 1, everything else is 0. So therefore, this is the pure zero quantum. We say it is the X component, X. 2 IKX ILX plus 2 IKY ILY is the X component of the zero quantum. Similarly, if I take the subtraction, 2 IKX ILX minus 2 IKY ILY, I get pure double quantum, the X component. See, therefore, everything lies in the density operator, that everything is a part of the density matrix. So when in the calculation of your density operator, if you get these various components, you know immediately what these ones mean to us. Where I've created a single quantum coherence, I've created a double quantum coherence, have I created a real component, have I created an imaginary component, all of these I will get to know from these elements. So therefore, it is crucial to understand the physical meanings of these product operators. Okay, IKZ, ILZ. This is something which you don't come across often. And this is called as the ZZ order. The two spins have the ZZ order. So this is not an equilibrium state. This is also not Z magnetization. This is called as ZZ order. This is a non-equilibrium state, but this is called as ZZ order between the two spins. It cannot be represented in the populations very easily, but often one tries to do that you represent these as populations here and populations here. This is what one tries to do, and everything else is not represented. So you write like this here in this case, that this one, the first state 1 and the state 4, these here you put populations, you don't put on the other one. This is called as ZZ order. Okay, thus the basis, the summary of everything what I described to you, thus the basis operators give a physical insight into the spin system. The IZ operator represents the populations and the Z magnetizations. IX and IY operators in a multi-spin system represent in phase single quantum coherences along the X and Y axis respectively. 2 IKX ILZ, 2 IKY ILZ represent single quantum coherences of K spin antiphase with respect to L along the X and Y axis respectively. Similar interpretations hold good for the L spin single quantum coherences as well. That means what I say, so if I say LX KZ, 2 ILX IKZ or 2 ILY IKZ, if I do that, I do the same operations as before. I only showed for some of those. IKX ILZ I showed, IKY ILZ I showed. But I can do IKY, ILY IKZ, turn the spins around, and ILX, IKZ, I can do that also. So accordingly, one can write similar representations in the density matrix, and you have the transitions represented there, antiphase magnetizations of the individual spins. Now, 2IKX ILY, 2IKY ILX, 2IKX ILX, and 2IKY ILY represent mixtures of double quantum and zero quantum coherences, and suitable combinations of these represent pure double quantum and single quantum coherences. Sorry, this is not single quantum, this is zero. Pure double quantum and zero quantum coherences. Okay, this is the mixture already written there. Suitable combinations of these represent pure double quantum and zero quantum coherences. Okay, that's what is written here again. 2IKX ILX plus 2IKY ILY represent X component of zero quantum coherence. KXLY minus KYLX, Y component of zero quantum. KXLX minus KYLY represents X component of double quantum. KXLY plus 2 KYLX represents Y component of double quantum. Notice here always that when you are talking about pure zero quantum or pure double quantum coherence, there is always this change in the sign here. This is a plus here and this is a minus here. Similarly, there is a minus here and a plus there when you are taking different elements of this. And 2IKZ ILZ represents a two spin ZZ order. Now, this is a complete list, complete table. I only demonstrated to you a few of the examples, but this is a complete table of all the 16 basis operators, all the 16 basis operators of the two-spin system. You can look at these, make combinations of any one of those, whichever way one likes, and then you will get the individual representations and the meanings of the individual basis operators. Okay, so this is for the record. So one can see wherever one wants to evaluate, it comes across any of this. Because why I'm showing all of this is, soon we will be going to evaluation of the individual pulse sequences, and we'll use product operator calculations. And we are not going to go write matrices there. We will simply write these operators, and okay, this operator represents this operator represents this, that's all. That's the way we go. Therefore, then becomes an easier thing to do. You can do a back of the envelope calculations kind of a thing. Much complicated NMR experiments can be analyzed in that manner. Now, we turn to a little bit more complex system, that is a three-spin system. Three-spin system has how many operators? 64 operators. We are not going to show all of that there, but I'm going to illustrate to you two of them. This also I showed earlier in yesterday's lecture briefly, but we'll do an example explicitly. Examine it a little bit more. So we have the three-spin system. We have the energy level diagram of this type. We have 8 energy levels. So how many transitions are there? 12 transitions. We can identify the individual transitions of the individual spins, and we can represent them as up arrow, down arrow for all the 4 transitions. Now, this particular term we are going to consider. This is now a 2-spin product. See, the 3-spin basis operators will have single spin operators, 2-spin products, and 3-spin products. In this 64 set, what I am considering here is the 2IKX ILZ in a 3-spin example, in the KLM. Okay, previously what we showed was 2IKX ILZ in the 2-spin system consisting of K and L only. So therefore, here it is the same operator, but in a 3-spin system, KLM. So therefore, what it means, I will have to IKX ILZ representation remains the same with respect to the X magnetization of the K spin, but the M spin, what does it do? What does it contribute? Because there is a coupling here. So all the 3 are coupled, right? So you have a K, L, and M. So you have K, L, M. So therefore, each of them is a now doublet of a doublet. So when you consider KX, LZ, it has a splitting due to the KL coupling. Okay, but the KM coupling is also there. The KM coupling leads to doublet of a doublet. Okay, so therefore, let us consider the K transitions here. The K transitions, which are the K transitions there? So these are the green arrows. The green arrows 1, 3, 2, 4, 5, 7, 6, 8. Okay, 5, 7, 6, 8. Now, in this particular case, what does 2IKX ILZ represents? We said, first of all, it represents antiphase magnetization with respect to L spin. Okay. that we have seen before. Here also it represents the same. It represents the antiphase magnetization of K spin, antiphase with respect to L. Therefore, if I consider the spins 1, 3, 2, 4, 1, 3, 2, 4 are here, 1, 3 and 2, 4. These belong to coupling due to the L spin. Therefore, what is the separation here? This separation is KL, JKL. JKL is the separation from here to here. Now, this entire doublet is split into two because of the coupling to the M. And the KM coupling is this. From here to here is the KM coupling, right? So this is again a KL coupling. This is a KL coupling. And now again, the two transitions here are 5, 7 and 6, 8. 5, 7 and 6, 8. If you notice here, due to the KL coupling, the two transitions have opposite sign. But the KM partners, if you see 2, 4 and 6, 8 or 1, 3 and 5, 7, they have the same sign. Now, if I want to write this whole thing in the matrix, what will be the size of the matrix here? The size of the matrix will be 8 by 8. So 3 spins. There are 3 spins. I have to represent 4 transitions. I'm not going to write the matrix here, but this is the 8 by 8 matrix. There will be 4 elements which will be non-zero. 4 on the top and 4 on the bottom. So if I talk the diagonal here, there will be 4 elements which will be non-zero and there will be 4 elements which will be non-zero. Okay, so here I will find wherever there is a 1, 3 element, or 1, 3, suppose the 1, 3 element is here, 1, 3 element it will be positive, and the 2, 4 element that comes from here to here, this will, if this is positive, this will be negative, 2, 4 element will be negative. Okay, and the 5, 7 element will come here, 5, 7 element will be positive, 5, 7 element will be positive, and 6, 8 element, 6 to 8 element, this is 6, 8, this will be negative in the 8 by 8 matrix. So this is what will happen. So 2, 4, 6, 8 have the same sign, 1, 3, 5, 7 has the same sign, and therefore we say the M splitting is what is called as the passive splitting. It is not an active, that we'll come to that later. So KL coupling leads to antiphase splitting, KM coupling leads to in-phase splitting, and that's why the term will appear like this: K6, 8 and 5, 7. The coupling constants can be represented in this manner. Therefore, we call this as X magnetization of K, antiphase with respect to L, and in phase with respect to M. In phase with M because 2, 4, 6, 8 have the same sign, 1, 3, 5, 7 has the same sign. So that splitting is in phase. Okay, go to this 3-spin operators, because in the 3-spin you have the 3-spin product. 3 is exactly the same as before, but now what else you have here? You have to show in-phase splitting, antiphase with respect to KL and KM. With respect to both we have to say. Okay, so therefore what you have here, so you see 1, 3, 2, 4, the transitions are the same. Okay, now I must also show here the signs. 1, 3, 2, 4, this is positive, 2, 4 is negative, 5, 7 is positive, and this is negative. This is negative, positive, positive, negative. Okay, so this is the way these things are. Now if I go next, I will have here 1, 3, 2, 4 has to be antiphase because it is antiphase with respect to L, but now MZ is also coming. The MZ also comes, therefore the K spin splitting with regard to M will also be antiphase. So therefore, what I should have here in these 4 doublets, see the KL splitting is antiphase, 1, 3, 2, 4 are positive and negative. Now 2, 4, 6, 8 are also opposite in sign. 2, 4, 6, 8 has to do with the KM coupling. 2, 4, 6, 8 is 2, 4, 2, 4, 6, 8. This is the KM coupling. And these ones also have opposite sign because this is now negative, this is positive. Therefore, we say this splitting is negative because it is antiphase with respect to M spin. That's why we say this is X magnetization of K spin antiphase with respect to both L and M. So this is how we get the pattern. I showed this kind of a pattern earlier in the previous class, but here is an explicit example as to how these things will show up. So similarly, if we were to represent this in an 8 by 8 matrix here, You can see here where with all these elements will be 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now 1, 3, 1, 3 is here. 1, 3 is positive. And 2, 4 is negative. 2, 4, this will be negative here. And 5, 7, let's say this right here, 1, 2, 3, 4, 5, 6, 7, 8. And 5, 7 is negative. 5 to 7, 5 is here. That's here, this will be negative. And for 6, 8 will be positive. 6 to 8, this goes here, this will be positive. So this is how it will show up in your 8 by 8 matrix. Everything else will be there. Of course, you write here the second part also here. I written only the one side of that. The other side of this will be the complementary of that one. So if I were to write 4 IKY, ILZ, IMZ, what will happen? I will get the same sort of a situation, except that I will get imaginary numbers. Yeah. Okay, so, and this is indicated therefore by the different signs with 3-spin system. So now you can expand this more. We can have also IKX, ILY, IMZ. What does that mean? Suppose I have IKX, ILY, IMZ. Now this I will write it as 4 because this is a normalization coefficient here. IKX, ILY, what was that telling me? That was telling me of a double quantum plus 0 quantum coherence. Okay. Now that one is now split into 2. It is split into 2 because of coupling to the M, and this will appear antiphase. These two components will have opposite signs. So therefore, that is the double quantum and 0 quantum coherences split with respect to the MZ, and that will have opposite signs. So this is what is the meaning of 3-spin operators. And the 3-spin ZZ order, so that is hardly come across. So therefore, mostly we will be dealing with this kind of a situation or this kind of a situation, or I4, IKY, ILZ, IMZ, that sort of a situation will be coming across. This also will depend upon whether it is a linear system or it is a linear system, means is KLM or KLM, depends upon what sort of a situation we have. If there is no M coupling, of course, there will be no change in that one. So this doesn't make sense in that situation. So either you have a linear system or you have a triangular coupling system, you will have this sort of splitting occurring there. Okay. So that is the end of 7. So we can start the 8, or maybe we should take a break here.
For linear system, that L will have the coupling from
L will have, but K will not have.
K
will not have
K and M will not have that.
Yes, yes.
So then the matrix will be still.
It will have only 2 elements. It will have K part will have 2 elements, but L put down will have 4 elements. The L will have KX is, let's say KX, LZ, MZ. LZ, MZ doesn't matter. It has to be LX. If it is LX, KZ, MZ, then it will be antiphase with respect to L. It actually will have 4 elements. But we can check that. So this is the clear.
Participant, if you have any question.
ये इधर है. This is in WebEx.
Yes, sir.
और उधर भी देखो Google में भी.
What's there? Please writing anything, no?
Tapos lang dyan sa these these two belong.
There are any questions?
to announce no for this register attendance. Test statement.
So now, having understood what these individual basis operators mean, now we have to calculate the density operator, right? Through the pulse sequence, we have to calculate the density operator. So that means the evolution of the density operator means evolution of the Cartesian basis operators. How these basis operators evolve under the influence of the various perturbations, like it can be the Hamiltonian, which can be free precession. If it is free precession, means it is simply under the influence of the Hamiltonian, or it can be the pulse. The pulse, there are two things which happen in a pulse sequence. One is the free evolution, other one is the application of the pulse. So these are the two perturbations that happen. So we need to understand how the density operator transforms under the influence of these two things. So first thing we will see is the evolution under the influence of the Hamiltonian. We are considering a weakly coupled spin system, and this product operator formalism has been developed for a weakly coupled spin system only. Okay, now how do we understand that? How do we know it is weakly coupled system? That is because you see this Hamiltonian here. This Hamiltonian, coupling Hamiltonian, is applicable only for a weakly coupled spin system. Otherwise, this is JKL IK dot IL. So it will have the IKX, ILX plus IKY, ILY. Those terms also will be there if it is a strongly coupled full Hamiltonian. For the weakly coupled Hamiltonian, this coupling part is approximated as 2 pi JKL IKZ ILZ. And the first one is the chemical shift Hamiltonian, that is the Zeeman splitting. So therefore, you have the Zeeman splitting here and the coupling part here. These are the two parts of the Hamiltonian. So the first term represents the chemical shifts and the second term represents the scalar couplings. So we need to evaluate the evolutions of the individual basis operators under the influence of the Hamiltonian. Okay, so this is typically illustrated here. Suppose I am considering the BS, a particular basis operator BS. And we had given earlier that how to calculate the evolutions. This is e to the minus, I had given with respect to the rho, with respect to the density operator rho. But in place of the density operator rho, I put the BS operator now, the basis operator. E to the minus IHT, BS e to the IHT. Okay, to you expand it, you get e to the minus IHZ plus HJT, BS e to the IHZ plus HJT. Now, this HZ and HJ, these two operators commute with each other. I suppose you know what it means commutation. Commutation, one should tell, it means if I write the commutation as like this, typically HJ, this commutator, this is called as, if this is equal to 0, then we say these two commute. Okay, what does this explicitly represent? I will write it as HZ, HJ minus HJ, HZ. This is the expansion of the commutator. When I write the commutator like this, if this operation is, this is equal to 0, then we say the two operators commute. And there are special properties when there's a commutation possible. So in other words, you can put them either way, whether you put HJHZ is equal to HJHZ. So I can turn them around. So without any problem if they commute. In the weakly coupled situation, this holds good, but this does not hold good in the case of a strongly coupled spin system. So since we are talking about the weakly coupled spin system, this is allowed, and therefore we can do various kinds of manipulations. So what I do here is I turn these two things around. In this case, I put the J first because and the Z I am putting here. Okay, but I don't do that here because it doesn't matter. So either way I can put. So I change one order here. E to the minus I, instead of HZ plus HJ, I write HJ plus HZ. Okay. Why do I do this? Because this will now bring in BS under the, I can split this into two operations. One is the evolution under the chemical shift. Other one is the evolution under the coupling constant. Okay, now this same thing I can write it like this, right? E to the minus I H I Z T into the minus I H Z T. Then I have here PS E to the I Z T E to the I H J T. See, now this one is looking like here, right? In the one operation, evolution under the chemical shift. And this second part will be the evolution under the coupling constant. Whatever comes out as a result of the evolution under the chemical shift, to that I apply the coupling Hamiltonian, the hyperrodent. I could have done the other way around also. Calculate the coupling Hamiltonian first, and then the chemical shift evolution. It does not matter. Either way one can do it. Okay, now let us consider the chemical shift evolution. So that is this here. Okay, if the chemical shift evolution, Hz is my omega k ikz, right? Hz is omega k ikz for the k spin. And this, of course, when you take the multiple number of spins, you have to take the summation of all of those. We are considering, but the k spin evolves under the influence of the k Hamiltonian. K spin does not evolve under the influence of the L Hamiltonian, it does not. Therefore, you have to consider only that particular part. If I am considering the basis operator kx, I should consider the Riemann part of the k spin. And that is the omega k ikz t, e to the minus ikz t, ikx e to the I omega k ikz t. Now here is one formula which you have to use. I will not derive this. The way this is obtained is that you expand this exponential operator as a series. You write e to the, generally you know this operation, e to the ix is equal to 1 plus ix square divided by 2 factorial and so on and so forth. Right? So this is the way you have this. If you have the minus sign, this keeps changing. By expanding all of this and then you have to combine the terms, you get this formula. Okay, so we'll take this, we will start from here. So this calculation itself can be a little bit longer. Now what is in this situation? The e to the minus I beta ix is given by cosine beta by 2. Of course, you should put here a unit operator. There is unit matrix. Minus 2 ix sine beta by 2. Cosine beta by 2 and sine beta by 2, these are, what do they contain? This contains, operator part I have taken it out. So this contains here omega k ikz. Okay, e to the beta ix is, in this case, this is the general form. When you have this operator, beta is, whatever is the beta here, that comes as cosine beta by 2 and comes as sine beta by 2, and the operator parts remains here. Oops. And what is the operator part here? Ikz. Okay, ikz is the operator part here. And omega kt is like the beta. Omega kt is equal to beta, right? So expanding this, when I write this, is that clear? So just look at it carefully. E to the minus I omega k ikz t, ikx, e to the I omega k ikz t. Now the operator, I want to write that in this form. If I want to write it in this form, the operator is ikz here, and omega kt is equal to beta. Omega kt is equal to beta. So e to the minus I beta ix, therefore I put this now down here. This is bs prime. First part is cosine omega k t by 2, that is cosine beta by 2. Of course, you have the unit number there. unit matrix, minus 2i sine omega k t by 2 ikz, and that is the same here. This instead of is, I have here ikz. Then I have this kx here, which is this kx, and on the other side I have cosine omega k t by 2 plus 2i sine omega k t by 2 ikz. Okay. These are numbers. I can put either ikz on this side or on this side, it doesn't matter, because these are numbers, these are operators. Therefore, numbers and operators can be shifted around. You cannot shift around the operators unless they are commutative. So this I can shift around in whichever way I want. Okay. So you expand this, when you expand this, so you get here cosine square omega k t by 2 ikx. Okay, how does that come? That comes from this to this multiplication. For the first term, this term gives you this, and you have the ikx here. And then I have 4 sine square omega k t by 2. That comes from this to this. But now I cannot move around the operators. Okay, so therefore the kz and the kx and the kz, they have to be maintained in the same order. Okay, they should remain in the same order. But the coefficient I can shift. The coefficient is sine omega k t by 2, and minus 2i into plus 2i gives me 4. Okay, the 4 sine square omega k t by 2, and kz, kx, kz, kx, kz, I have to maintain in the same order. Okay, and then I have minus I sine omega k t, so here is a commutator there. So how did I get this? There are two terms here, kz, kx minus kx, kz. Kz, kx, and if you do the other way around, you have the kx, kz. So we'll have two terms here. Minus 2 sine omega k t kz, kx, this is the first one. Okay, and this one cosine omega k t to this one, and 2 multiply kx, kz. And together you have this I sine omega kt, because this is 2 sine omega, it will be 2 sine omega kt by 2 cosine omega kt by 2, and that will be equal to sine omega kt. Therefore, you have sine omega kt and you have the commutator kz, kx. This is basically two terms. Therefore, there will be a total of 4 terms. So the two terms are combined into one here as a commutator. Okay, now let us try and calculate this kz, kx, kz. So here all of them belong to the same spin. Remember, I have 3 spin product here. There is a 3 spin product, kz, kx, kz. Here I cannot take direct product. Direct product has to be taken when the 2 spins are different spins. Then only it increases the matrix size. But here it is simply kz, kx, they are all of the same spin. Therefore, I take simply the multiplications of all of those. Put the kz 1 minus 1 here, kx is 1 1 here, and kz again 1 minus 1 here. So if I multiply this, what I get? Minus 1 by 4 ikx. So this is ikx, but with a minus sign. So that is half, you take it away, so you get minus 1 by 4 ikx. So this product is simply equal to ikx, 1 by 4 ikx. So this will simplify your previous term there. So therefore what I get here is cosine square omega kt by 2 ikx minus sine square omega kt by 2, and now I have here ikx, because there is 1 by 4 and there is a 4 here, therefore 4 cancel, you get ikx here only, plus sine omega kt iky. And how did I get this iky? Because that is the commutator. The commutator, this kz, kx is the commutator. Okay, there is a cyclic rule here. So the kz, kx commutator is equal to minus iky. Okay, so the minus iky into minus iky, so you get here, or ky, iky. So you get here plus iky and sine omega kt. See, therefore, you see the formula became very simple. What is this here? Cosine omega square kt by 2, kx minus sine square omega. So you put these two together, kx, this becomes cosine omega kt. Cosine omega kt is basically cosine square omega kt by 2 minus sine square omega kt by 2. This is simple arithmetic. This is algebra. Okay, or trigonometry or whatever. Okay, so therefore cosine omega kt ikx, because ikx is the same in both, and sine omega kt iky. Okay, so very simple process, right? So this is a rotation. This is telling you what the kx is actually rotating as into this term. So therefore, if I have the x here, this rotates under the influence of the chemical shift. If here the picture is showing capital omega there. So it rotates in this manner. So you generate a kx component and a ky component. So it's simply precession in the transverse plane. See, evolution of chemical shift meaning what? It is a rotation in the transverse plane. Kx and k. Kx goes to kx plus ky. Ky goes to ky minus kx. Now suppose I were to start from iy, I get iy and minus ix. Okay, that will probably come in the next one. This is scalar. Okay, so therefore, this picture is shown to indicate what all the transformations are happening. Now, if you look at what are the axes here, the three axes are, you represented the operators. X-axis represents the X magnetization for a single spin. The Y-axis represents the Y magnetization. The Z-axis represents the operator, the chemical shift Hamiltonian. Chemical shift Hamiltonian is IZ. Therefore, these three operators, IZ, IX, and IY, they form a rotation group. There is a transformation. By looking at this figure, I can immediately say which term is going where. If I consider the IX term, it produces KX plus KY. If I start with IKY, I will get IKY minus IKX because it is going in this direction. If I start with minus IKX, I will get minus IKX minus IKY, right? So in the same manner, if I start with minus IKY, I get minus IKY plus IKX. So therefore, this is a rotation around this. This is a rotation indicated by this circle here. So therefore, evolution under the chemical shift is rotation around the z-axis. Rotation around the z-axis is the transverse magnetization is rotating in the xy plane. So this is the simple formula. We are going to use this simple formula later on. Let's do the same thing for a coupling Hamiltonian. Scalar coupling Hamiltonian, the Hamiltonian is now e to the minus 2 pi jkl ikz ilz kx e to the I 2 pi jkl ikz ilz t. Okay, the coupling Hamiltonian is kz lz. Okay, the shift Hamiltonian was kz only. So here the coupling Hamiltonian is kz lz. Therefore, we are putting here jkl ikz ilz. So you put this, now again I have to use this formula here. So this formula we are, I'm not deriving it there, but I will simply use this formula. In the same manner it was done e to the I beta ix. So you do the same thing here. When you do this formula, you can use this formula e to the minus I 2 pi jkl kz lz t is equal to cosine pi jkl t by 2 minus 4i sine pi jkl t by 2 ikz ilz. So this is exactly the same way it goes as in the case of the previous one, e to the minus I beta ix. I expanded the whole thing in terms of the exponent and the power series, but there is only one operator was there. Here I have to use both the operators. You can use matrix representations of the kz delz product. Now kz delz product means you have to use the direct product. These are 4 by 4 matrices. Okay, whereas in those cases it was a single 2 by 2 matrix. You can do that, but so without having to going into that, we can simply use this formula. Okay, e to the minus I 2 pi jkl ikz ilz t is equal to cosine pi jkl t by 2 minus 4i sine pi jkl t by 2 ikz ilz. And this one actually will give me bs double prime. This is the bs double prime. A lot of algebra is skipped here in the sense that I put this formula here and also here. Okay, putting these two formulas, finally what I will get here is bs double prime is equal to ikx cosine pi jklt plus 2 iky ilz sine pi jklt. Because this, if I want to draw this algebra, that itself will go to 1 hour. Okay, so we don't need to do that. If one should know how to do it. Once you know how to do it, then of course you can take it as an exercise. You can do that exercise and find out this, prove this formula. Okay, but this is the useful formula here. Under the influence of the coupling Hamiltonian, the kx operator develops as ikx cosine pi jklt, but notice it generates an anti-phase magnetization of the k spin with respect to L. The in-phase magnetization remains as kx, and I also get a term which is the Y magnetization anti-phase with respect to L, and that is with the coefficient sine pi jklt. Okay, so this is for so far that was for the kx operator. Now we can do the same exercise for the ky operator. Ky operator gives you cosine omega kt iky minus sine omega kt x, because you see, you remember this picture. Ky goes to ky minus kx. Iy, it goes with this rotation, therefore I get a minus sign there. So therefore you get a minus sign there. IKY minus sine omega kt kx. And similarly for the Bs double prime, which is the coupling Hamiltonian, gives you IKY cosine pi jklt minus 2 ikx ilz sine pi jklt. So in the previous case, what I had a plus sign here. The kx evolving gives me the plus sign and the antiphase magnetization of k with respect to the y magnetization of k antiphase with respect to L. If I start with y, then I have a minus sign here. So once again, this can be represented in the form of sort of a rotation group. I will show you that. So for the basis operator 2 ikx ilz, the evolution under the coupling can be written as, I am writing this just the formula here, okay. All of these can be calculated in that manner. This is the cosine pi jklt 2 ikx ilz plus sine pi jklt iky, okay. And for the 2 iky ilz, I get cosine pi jklt 2 iky ilz minus sine pi jklt ikx, okay. So this is just the final result of this calculation. This can be easily understood in terms of the rotation groups once more. I write here two rotation groups. Now what are the axes of the rotation groups here? Two groups here. IKZ, ILZ, I put it along the Z axis. And that is the Hamiltonian. The Hamiltonian is put along, so it's basically a rotation around the Z axis. Rotation around the Z axis, because it is influencing, it is evolving under the influence of the coupling Hamiltonian. So that is represented here as 2 IKZ, ILZ. Okay. Now, what are the other elements there? What is the transformation that are happening? If I want to start with Kx, you notice I got Kx and 2 IKY ILZ, right? The previous formula. So if I started with IKX, I got IKX, IKY, ILZ. Okay. If I start with IKY, I get IKY and minus 2 IKX ILZ. This is under the influence of the coupling. Okay, let's look at that here. If I start with IKY is here. So I get, if I go with IKY, I get IKY minus 2 IKX ILZ. The coupling Hamiltonian remains on the Z axis. So rotation around the Z axis here represents this manner. So the one operation which was, for one formula which was given was here, Kx rotating into IKX and 2 IKY ILZ. IKY rotating into IKY and 2 minus IKX ILZ. You can extend this, that if I start with 2 IKX ILZ, what will I get? If I start with 2 IKX ILZ, I get this. IKX ILZ and IKY. And that's what was there. If I start with the 2 IKX ILZ, I get IKX ILZ and IKY. Right? So these were the two operators. And IKY ILZ, I get 2 IKY ILZ minus IKX. So that is the same thing here. So if I start with 2 IKX ILZ, I get 2 IKX ILZ and IKY. If I start with 2 IKY ILZ, that is this one here, I get 2 IKY ILZ and minus IKX. See, therefore we say these ones form a rotation group. The elements which are present in this figure form the rotation group, one rotation group. Elements which are present in this figure, they form another rotation group. So therefore, if you have this picture in your mind, ready in your mind, then you can immediately write down what is the term which I am going to get when I consider the evolution under the chemical shift Hamiltonian or the coupling Hamiltonian. The previous one was the coupling Hamiltonian. Here I have the, previous one was the chemical shift Hamiltonian. This is the coupling Hamiltonian. Once again, let me repeat, the Hamiltonian, part is put along the Z-axis and your basis operators are put along the transverse, in the transverse plane. The IKY, IKX, IKXILZ, IKY, these are all my basis operators. I am putting them in the transverse plane to indicate which ones are transforming into another within the group. They transform into each other. So to indicate that, so you form a rotation group like this. So therefore, by looking at this, you can immediately figure out starting from where you will reach. Okay, so this was an elegant description of the evolutions of the basis operators. Okay, now rotation by pulses. Now we have to consider rotation by the pulses. So far it was the Hamiltonian. The pulses are the ones which actually cause rotations. They are simply rotations only. And this is represented in this manner. RQ, BS, RQ minus 1. R is the rotation, BS is the basis operator, and Q can be X or Y. So I apply the pulse along the X axis or the Y axis. Okay. So the same formula applies. So for a 90-degree pulse, the transformation will be Rx pi by 2 Iz Rx minus 1 pi by 2. I considering here the BS is equal to Iz. See, the magnetization, Iz is the magnetization along the Z-axis, right? In this case. So if I consider that particular operation, so I put here a rotation along the X-axis, Ix pi by, Rx pi by 2, Iz Rx minus 1 pi by 2. This is the 90-degree pulse. So what I do here, I put these three matrices of the individual ones. Okay, these are rotation matrices. So Rx pi by 2 is 1 minus I minus I1, 1 over root 2. Then this Iz is half 1 0 minus 1, and similarly Rx, the inverse of this is 1 by root 2 1 I1. So these are simply rotation matrices, right? Simply rotation matrix is e to the minus I beta. E to the I minus I beta is written as the rotation matrix for a one spin system, and that will be simply represented in this manner. Okay, so therefore this gives me minus Iy. This gives me minus Iy. So the X pulse on acting on the Z axis is giving you minus Y, minus Iy. So again I put it as a rotation group here. So the rotation can happen along about any axis. Okay, the rotation can happen from Z to the Y or Y to Z or X to Y, anything can happen. Okay, it is so Iz to 90X gives me Z to minus Y. If I start with Y, I have applied 90X pulse, where does it go? It goes from Y to Z. If I apply 90X pulse on Y magnetization, it goes to positive Z. If I apply 90X on a minus Iz, it will go to Y. Right? Z goes to minus Y, minus Z goes to plus Y. So that is for this picture has drawn very nicely. One can see this. This is with respect to the rotation around the x-axis. We can draw similar pictures for the rotation around the y-axis, for the pulse along the y-axis, and the various rotations that can happen in this. Okay. Now, if I consider Bx is equal to Iy. Okay, that was the Z matrix. That was the operation on the Z element. Okay. So for a 90x pulse, the odd will be the transformation. So what you have to put here? Rx pi by 2, Rx Iy, Rx minus 1 pi by 2. It is the same multiplication here. I put here Iy, this is Iy here, and these are the two rotation matrices of the pulses, pi by 2 pulses. And that gives me equal to Iz, 1 0 0 minus 1. This gives me Z. So that means 90x pulse on Iy rotates this to Z. Okay, so therefore Iy, so therefore you see these are very simple operations now. Eventually we have to remember only this. Eventually we have to remember only these operations. How the things are moving from where to where. These calculations you may forget. Okay, but there is a basis. These actually provide the basis for how we have obtained this. Physically also one can understand these rotations can be simply understood by hand waving arguments. Okay, for a Y pulse. For a Y pulse, that is so far we looked at the X pulse. Now the Y pulse, the similar figures apply. So the Z magnetization goes to X for the Y pulse. Okay. And the minus X goes to Z. Minus X goes to Z. And X goes to minus Z. see, x goes to minus z. If I apply a y pulse, and you can remember this picture. So all this should be in the head. So these pictures, if they are in the head, so then immediately we can see which rotation is causing which transformation from where to where. Okay. Now I apply, this is another thing which was considered. So we consider Iz, Iy, and now I am doing Ix also. The same operation. So what we get here, once at the end, you get here only Ix. Nothing has happened to Ix. Therefore, you apply a X pulse on an X magnetization, nothing happens to it. It stays there. So basically, we are saying Ix is invariant under X pulse. Of course, if you apply a Y pulse, it does cause a change. That is indicated by the rotation operators. So all this has a mathematical basis. For all these transformations which are there, rotations which are there, they can be explained in a mathematical manner. Okay. Now, for multi-spin basis operators, so far we consider IKX, IKY, IZ, two spin operators. But we have the two spins are independent.
Some error there, so
Huh?
student का एक ये था, we were facing some problem.
कुछ मैसेज था?
हाँ, चला गया. देखो तो चेक बॉक्स. Huh? But it came and then okay. Continue.
Okay. All right. So now let us consider, so far we looked at the one spin system. But you can, in the multi-spin systems, what happens? Because your basis operators are more complicated. There are many basis operators, two spin products, three spin products, and so on and so forth. Now, you can apply the rotation pulses to the individual spins separately because they are independent spins. They are independent spins, therefore you can apply the pulses separately. Okay. So therefore, when you have a situation like that, we consider, let us say, an operator term which is 2IKX ILZ, the basis operator 2IKX ILZ. What does this represent? This is representing a antiphase magnetization of K spin, right? 2IK, which you already saw. Now to this I am applying a 90XK, 90XL. I am applying a 90X pulse to both K and L spins. Okay. Now nothing happens to X because it is invariant under X rotation. Therefore, Kx remains as Kx. What happens to Z? Z goes to minus Y. Okay. So therefore, it becomes 2IKX ILY. So you see now what I have done. We have converted the single quantum into the mixture of double quantum and zero quantum coherences. We explicitly saw this earlier, right? 2IKX ILY was representing a mixture of double quantum and zero quantum coherences. So therefore, by applying a simultaneous pulse on both the spins with the same phase, X spin, I am getting minus 2IKX ILY. A coherence transfer from single quantum to zero and double quantum coherences. Of course, you can change the phases of this. In case of heteronuclear systems, I can also apply one along x-axis, one along y-axis. It does not matter. I can apply 90xk or and a 90yl. I can do that also. If I apply 90yl, then where does this z go? Z goes to x. If I apply 90x pulse, then z goes to x. Then I will get here 2ikx ilx. Right? If there were two heteronuclear spins, if I have different phases here of the pulses, one along x, one along y, this you can always do. We always do this in the case of inept pulses. I will explicitly show these calculations to you. You can apply along the x and the y for the two individual spins on separate axes, on separate either the x or the y. Then you can actually create different kinds of transfers. So you get here mixture of double quantum and zero quantum. Even if it is ILX, then also it is a mixture of double quantum and zero quantum coherences, as we saw before. Okay, so if I already shown this here. If I apply now the same turn, I apply 90 Y pulse. Apply 90 volts to both. Apply a 90 pulse along the Y axis to both the spins K and Y. So 2 IKX ILZ, what does it go? X goes to minus Z and LZ goes to X because of the 90 Y pulse. Takes you to L, X and Kx goes to minus Kz. So I got here minus 2 IKZ ILX. What does that mean? Here it was, both are single quantum coherences. Both are single quantum. But here it is K spin, here it is L spin. So therefore you see, application of the pulse, application of a 90-degree pulse to antiphase magnetization causes a coherence transfer from one spin to another spin. K magnetization has been transferred to the L spin. I mean, this is exactly what you do in the case of the inert sequence, right? You apply 90 X pulse at the end to both the proton and the carbon. We apply 90 pulse to both the spins. And then you do a coherence transfer from the proton to the carbon 13. So we do that same thing is happening here. From K to L transfer is happening when you created the antiphase term first, created an antiphase term, and to that antiphase term we apply 90 pulse along to both the spins along one axis. Then it causes the single quantum transfer of coherence. In the if I applied along the x-axis, I contributed to the multiple quantum coherences. If I apply an orthogonal axis, that is, if the transverse magnetization is along the x-axis, apply a pulse along the y-axis, then it will cause a coherence transfer between the single quantum coherences. If I apply along the same pulse, same axis, I create double quantum and zero quantum coherences. Okay, and then this is causing a coherence transfer. Now here, suppose I apply pulse to only one of the spins. I don't apply to the second. And this I can do if the two are heteronuclei. If it is a single, only proton only, you will have to apply selective pulses. But in heteronuclear situations, you can apply to only one spin with your choice. So therefore, if I have 2 IKX ILZ, apply 90 pulse only to K spin along the y-axis, then I get ZZ order. ZZ order is used basically to store information. During the pulse sequence, what you do is you don't want the magnetization to lose. Decay, you don't want the decay to happen. If the magnetization is on the transverse plane, it decays because of T2 relaxation. So therefore, you want to save this decay, you want to store the magnetization somewhere, you convert that into ZZ order. So you get both along the Z axis, 2 IKZ ILZ, this is the Z order, that will not decay. And later on, you can bring it back to the transverse plane to observe. So these are all the tricks of the pulse sequence design. So you can do it whichever way you want. So that is how you have to optimize what pulse should be applied where. Okay. So this I already explained to you. 2 IKX ILZ, if I apply 90 Y pulse only to L spin, IKX ILZ term is there, I apply only to L spin. So this gives me 2 IKX ILX, which is again a mixture of double quantum and zero quantum coherences. Similarly, 2 IKY ILZ, apply 90X pulse to both the spins, I cause a coherence transfer from single quantum to single quantum K to single quantum L. Okay, so this represents conversion of antiphase Y magnetization of K spin into antiphase Y magnetization of spin L. This is referred to as a coherence transfer from spin K to spin L. In general, it is seen that application of RF pulses to antiphase magnetization in multi-spin systems causes coherence transfer among the spins. This forms the basis of many multipulse experiments in homo and heteronuclear systems. Remember, when we were considering the evolution under the Hamiltonian, there is no coherence transfer. Hamiltonian evolution, free precession, cannot cause a coherence transfer. To cause a coherence transfer, you need a pulse, you need an RF pulse. Only then you can cause coherence transfer. And that is the basis of the various kinds of pulse sequence designs. So, okay. So now this is the summary. I'm repeating this once more. All the things are put together here. The chemical shift term, this is the chemical shift evolution is Z. Hamiltonian is put along the Z axis. This is the Hamiltonian, the Z axis. These are the individual basis operators here, Ix, Iy. These are the three operators, right? For the single spin, I have the unity operator, and then I have the Ix, Iy, and Iz. Iz is actually the Hamiltonian, and Ix and Iy are we're considering as the basis operators. Okay, so the transformations happen like this: x transforms to y under the inverse, y transforms to minus x transforms to minus y, and minus y transfers to x. So there will be components. Any particular component of the magnetization, if it is present here, so then you will have components here and component there. Okay, so if I have a magnetization component here, it will have a component here and a component there. This is what we saw when the evolution was considered of the individual basis operators under the influence of the Hamiltonian, the Zeeman Hamiltonian. So Z rotation, Ix operator transformed partly into Ix and Iy. Iy operator transformed partly into Iy and to minus x. So this is the summary of all of that with the Jacob, with the chemical shift Hamiltonian. These two are the summaries of the scalar coupling Hamiltonian. Now here it is Hj. Right, this is the Hamiltonian Hj. Hj is give Ikz ILz, that is represented along the z-axis, and the two spin products which you are considering, and the single spins, all the things forming groups here, rotation groups. So if I start and influence, if I consider the Ikx basis operator and consider its evolution under the Hamiltonian Hj, then it transforms as Ikx, partly Ikx and partly to Iky Ilz. Okay, notice here there is no coherence transfer. All the terms which are written in the transverse plane, all these represent K magnetization only. They don't represent L magnetization. Right? There is no transfer from K magnetization to L magnetization. It always remains within that. It transforms within themselves as in phase to antiphase, antiphase to in phase, and things like that. The in phase goes to antiphase, antiphase goes to in phase goes to antiphase, antiphase goes to in phase, depending upon how much is the time that is given to you. For that, pi jklt, the t factor is there. All right, pi jklt, this is the beta term. How much is the rotation? How much is the rotation angle? The rotation angle, if it is 90 degree, it goes all the way from here to here. If it is not 90 degree, it is somewhere in the middle here. So therefore, you will have the components here for on the two axes. Similarly, depending upon that angle of rotation around this Hamiltonian, you will get different components which are present here. That is what was indicated in the previous slides there, right? Yeah, all these terms. So these are the coefficients. These are the coefficients. To that extent, you will see how these things are rotating. That is the angle of rotation. Omega kt is the angle of rotation. So here it will be the angle of rotation. So this will be the kind of terms which you will get here in the representations. Okay, so this was the chemical, and then you have this, as I said, chemical coupling Hamiltonian here. So here the ky goes to kxlz, 2ikxilz goes to ikxlz and ky, and ky similarly ky and kxlz. The signs one has to remember. Consider a rotation in a particular direction only. You do not mix up the rotation. It has to be the same anti-clockwise rotation. Always you treat with anti-clockwise rotation. They represent the transformations of the individual operators. Okay, so I think that the rotation by the pulses. So rotations can be along the x or the y axis. We don't talk about the rotation around the z axis. Rotation around the z axis was what? Of course, we did consider that. Rotation around the z axis was basically chemical shift evolution. Your Hamiltonian was omega k ikz. So therefore, rotation around the z is actually chemical shift evolution. Rotation around x and y, these are from the pulses, because you apply the pulses along the x and the y directions or anywhere in the transverse plane. Therefore, when I say pulses, I focus attention only on the transverse plane, x or the y. And therefore, and then it indicates how the various individual pulses transform here. So if I take, what is the rotation here? The rotation is here x rotation. X rotation transforms z into minus y partly. Of course, if the rotation is 90 degree. If the rotation is not 90 degree, you will have somewhere here. So you will have a component here and a component there. Okay, cosine beta, sine beta. So therefore you will have these components. If I start with minus y, I goes to minus z, and I start with minus z, I go to plus y. If I start with y, I go to plus z. So therefore, when you write the product operator evolutions, you will have to see what signs you are using, because this is very important. The sign, it has to be maintained properly. And in this case, the y rotation takes z to x. Y rotation, once again, this is anti-clockwise. Okay, rotation, when I'm talking, the arrows you should see, the rotations are anti-clockwise in the sense. So therefore, z goes to x, x goes to minus z goes to x, and then x goes to z here. So z goes to x, and of course the reverse also, minus x goes to z. Okay, I think that is the end of this lecture. So should we go continue?
I think let them see this part.
Let us see this part. Right now? Yes. What do you feel?
No, I'm fine with that, sir. So I have all the 16 lectures ready.
Let them dissipate little bit. But what about participants?
I think sir, he has to connect now. He has muted them now. Yes. There are participants to connect.
Hello?
Yes, yes.
Unmute
who-
participants, what, how they feel?
No, I'm in a meeting.
Useful. Continue করবে আর তে
Continue.
better not to na.
Yeah, it's, I mean, either way I can find. So that is,
No, but I feel they may be.
So, sir, what is your next lecture? Is
put that in
Yeah.
also.
so that let us see if it is very correlated now. I think this is now we have already told about all these T pulses and all these things. na?
Yeah.
So I think that what is that? Let us,
I think in the next ones, I'm actually going to do calculations, explicit calculations.
so that's and then we will start.
Start next phase class.
Yeah,
So this is the summary of all those. See,
Yeah.
finally, these are things which you remember.
yeah.
You need only these many.
Right.
After we use these 6 formula, then you can.
Really, they should be able to tell. Na?
Yes.
Hello, participants. So if you have any doubt or the queries, you can tell. And also you can suggest that whether we should continue or
We make a stop here for the,
we'll stop here and then we will continue in the next on Friday.
what is your feeling?
What is your opinion? Because still we have some time left.
Yeah. Did we go fast or was it okay?
Yeah,
The
no,
speed
it was
was-
okay. It was okay. Okay, you can type in the chat box what you should do.
Continue on Friday.
Continue on Friday. Yeah, I think I was
It's also like that. Take it in such a way.
Yeah.
Okay, fine. And then you make a revision of the things and then Friday again, maybe we can start.
Yeah, and again at
Yeah,
4
so I think what they should do, can suggest an exercise for them. See, many of these formula, I initially showed how to calculate.
Yeah,
Subsequently, I just indicated the formula. But you may try to derive them.
yeah.
As an exercise, you may want to derive at least one of those. If you derive one of those, then you know how to derive the others.
Yes.
So one formula you can derive.
That is a good exercise.
Yeah. See, for example, in the blue, I put it in the blue square box. If you remember, e to the minus I beta ix is cosine beta by 2 into ix minus sine beta by 2. This I wrote cosine beta, you need to put it minus sine beta by 2 ix. Try to derive this formula. If you derive this formula, then everything else will follow from the same. In the same manner, you can calculate. Because you have to remember the properties of the spin operators, that ix square is equal to 1. Okay, that becomes important. This is a hint I am giving you. you wrote ix square is equal to 1, ix cube is equal to ix. Okay, so therefore, when you do the power series expansions, it will go on, right? ix square, ix cube, ix 4s, all of those things. But there you have to make use of this relationship that ix square is equal to 1. And therefore, ix cube becomes equal to ix. Therefore, everything will get condensed into two terms only, ones which are dependent on ix, ones which is not dependent on ix. And that is the first term cosine beta by 2. The one which is dependent on ix becomes the second term sine beta by 2 ix. In fact, I already told you how to calculate it.
Okay, good, good exercise. I think they are getting saturated actually. Yes.
Actually,
No problem.
Actually, it is much.
It's too
enough,
much.
right? Much is enough. Yeah.
It's enough for today. Friday we can.
Yeah.
okay.
Till Friday we can have an exercise of this. That's
So let them try to calculate.
Yeah.
Let them try to calculate.
good. Okay, thank you. Thank you very much.
Thank you. Thank you. We'll stop here. And then on Friday at 4 o'clock again, we'll continue. Thank you.